Hello, this is Teach Nichols, and this lecture is on solving multi-resistor circuits. So if you have a complicated circuit with more than one resistor in it, how can you figure out any of the circuit variable values and then maybe make predictions about what we would observe if we were looking at that circuit? So solving a circuit can refer to finding all of the values of the variables for the entire circuit and for the individual resistors, or maybe just bits and pieces. Maybe you're interested in just the power output at a specific resistor. But regardless of what you're interested in finding, you're going to try to remember that some of the fundamental tenets and laws have to hold true as you try to come up with information or solutions for parts of your circuit. Number one, remember that Kirchhoff's junction law must apply in every junction in any circuit. That law is specifically going to tell you what's happening to the current as it goes into and out of any junction via conservation of mass. Kirchhoff's loop law applies for voltage in any loop in any circuit, and that again comes from conservation of energy. There is one more rule of thumb that I find handy. It's not been written into an official law, but I find it really useful. If you end up solving an entire circuit, knowing everything about every resistor and everything that's happening at the battery for the circuit, you will find that the power output at the battery is equal to the power usage, the sum of the power usage of all of the individual resistors. In other words, the amount of energy per second the battery is spitting out is used up every second in the resistors, which should sort of make logical sense and also follows with conservation of energy. So this isn't an equation you'll find in your equation sheet, but will be true for every circuit, no matter how the resistors are connected, that the total power is equal to P1 plus P2 plus P3 plus as many resistors as you have. So you can solve circuits with Kirchhoff's laws and simultaneous equations, but I find this slow and error prone. Or you can solve circuits using a combination of logic, proportional reasoning, and a handful of handy equations, which I tend to find a lot faster, especially if you're just looking for an isolated piece of information, so more useful on the AP test in my opinion. The rest of the slideshow is going to talk you through kind of some other ideas that you need to know in order to use this, and then show you how we do this using something called a VIRP table. So when you look at any circuit that has more than one resistor in it, you should notice that there are fundamentally just two ways that you can connect more than one resistor to each other. The first way is known as in series. If you connect two resistors in series, the electrons have to pass through all of those resistors before they continue on through the circuit or before they return to the battery. So this is an example of two light bulbs connected in series. If an electron wants to get back to the battery, it's got to go through both of those light bulbs before it returns. This would be a schematic diagram of four resistors connected in series. And you can see again the single loop that is created when you connect things in series. When you connect things in series, logically, it should follow that there is the same current through all of those resistors. According to the junction rule, there are no junctions. Therefore, the current into each resistor is same as the current out and the same as the current into and out of the battery. However, the voltage used at each of these resistors is going to be sharing the voltage from the battery, right? We have a single loop in this, therefore we gain energy at the battery and we lose energy at each of those resistors. Therefore, we're basically summing the voltage used at the resistor should sum to the total voltage of the battery. So that's kind of conceptually where we get using our loop rule. If you have this kind of circuit, the voltage that is used at each resistor is going to be proportional to the resistance. In other words, if a resistor is harder to get through, it gets a higher percentage of the voltage or the energy of the battery. That comes from Ohm's law. I equals V over R, but if I is the same, then there's a linear relationship between V and R, so we're going to have more voltage used as we have a bigger resistor. Ultimately, that's going to mean that if we have a pure series circuit like this, that light bulb ends up brighter, the higher voltage, higher resistance bulb, because it's getting more voltage with the same current. The second way to connect resistors is called in parallel. And when you connect two resistors in parallel, that means that the electrons actually have a choice of which path they're going to take to get back to the battery. They can go through one resistor or the other resistor, but they won't necessarily go through both of them. Here's a schematic of 3 resistors wired up in parallel with a battery. When you connect resistors in parallel, you actually end up using the same voltage in each resistor according to the loop rule, right? There are sort of 3 little loops there. There's a loop for each resistor that only includes the battery and that resistor. Therefore, whatever energy we gain at the battery, we have to dump all of it in every single one of those resistors. It's different electrons, but they're going to use all of their energy. The current, however, is going to be split because there are junctions in this circuit where the electrons will choose whether they go to R1, R2, or R3. And when the current splits, you should find that proportionately more current goes to the lower resistor according to Ohm's law. So if the voltage is the same for all 3 of those resistors, then the higher the resistance, the lower the current ends up being. Ultimately, if you're looking at 3 bulbs connected in pure parallel circuit like this, since they have the same voltage and the bulb with less resistance has more current, it's going to be the lower resistance bulb that is brighter. So this is kind of interesting because that means that brightness itself or power can't really be tied to the resistance because it really depends on how the bulb is connected. And if you change the way bulbs are connected, the brightnesses of the bulbs are going to change as well. So before we get into the nuts and bolts of solving these circuits out mathematically, I want to talk about a few conceptual differences as well between series and parallel circuits. When you connect more than one resistor in series with each other, you should find that the resistance of the circuit, or the resistance of that chunk of the circuit at least, increases with each resistor that you add in series. If you think about our resistivity equation, it should make sense because adding more and more resistors in series is almost like adding length to the resistor, and we know that length has a linear relationship with resistance. There is actually an equation that shows this on your equation sheet. That equation says R sub S, which stands for the resistance of resistors in series, is equal to the sum of the individual resistors. So that's the sum of R sub I for as many resistors as you have. So if you have 3 resistors, you just add them up, and that should tell you the resistance of the chunk of the circuit with those resistors in it. What this kind of ends up meaning is that as you add resistors in series in a circuit, you're increasing the resistance of the circuit. You, generally speaking, lower the current in the circuit because there's an inverse relationship there, and that means less overall power. This is not a great way to connect things like in your house or when you're building things in general, because every time you throw a new device in there, it's going to reduce the current for all of the devices and make everything in the house or whatever get dimmer. In addition, if one of those devices breaks, now we have an open switch and none of the electrons can get to the other devices before or after. So we don't tend to use a ton of series circuits in practical life. Parallel circuits are a lot more useful. And one interesting thing about them is that the total resistance of a parallel circuit is actually less than any of the individual resistors. This is a little bit hard to get your brain around the first time you think about it. But if you remember that in our resistivity equation, as we added surface area or width to a resistor, we actually decrease the resistance. It's like there's more doors, more pathways, more ways for the electrons to get through. So you can think of 2 resistors in parallel as basically one big fat resistor because there's multiple pathways for those electrons to get through. So adding resistors in parallel actually decreases the overall resistance of a circuit. There is an equation that allows you to shortcut calculate the resistance of a circuit if you know the individual resistors in parallel. It's a little bit harder to use than the other one, but it's essentially the sum of the reciprocals of the individual resistors is equal to the reciprocal of the total resistance of a circuit. So if you have 2 4-ohm resistors, you would say 1 over 4, which is 1/4, plus 1 over 4, which is another 1/4. Add those together, you get a half. and then you take the reciprocal of that to figure out what the resistance of the circuit is, so you end up with a resistance of 2. So adding 2 4-ohm resistors makes a resistance overall of 2, which is less than the individual resistors were, because we've increased the area. So less overall resistance in the circuit means that we actually get more and more current every time we add a resistor in parallel. It actually forces that battery to spit out extra current and extra power because we have more pathways for the circuit for the electrons to go. This is how we tend to wire things up in our houses for multiple reasons, but one of which is that we don't want each device to affect the other devices in the circuit. So when you add different pathways, the new pathway does not necessarily affect the pathways that existed there originally, and you don't make other things dimmer when you add new devices. Solving a circuit using this combination of logic and reasoning and equations and a tool known as a VIRP table to organize our information. So we have a very simple series circuit here with 2 resistors and a 12-volt battery. A VIRP table, of course, stands for voltage, current, resistance, and power. And I add 1 column for each device in my circuit. So if I have 2 loads, I have R1 and R2, they each get a column. And then I always put a column for total, which sort of reflects the entire circuit as a whole. First thing that you do is just fill in the known values. So R1 is 100 ohms, R2 is 200 ohms, and I know that the total voltage provided by the battery is going to be 12 volts. From here, it's a combination, like I said, of logic, reasoning, and equations to figure out where we go next. Usually on series circuits, I jump straight to, well, I know the total resistance in the circuit because I put 2 resistors in series. The total resistance is going to be 300 ohms. It just adds up when they're in series. So the nice thing about this is I now have 2 known values in my total column. Whenever you have 2 values in a column, you can solve the rest of that column using Ohm's law and the power equation. Ohm's law is I equals V over R. So we can go ahead and plug in 12 divided by 300, and we end up getting current. The total current in my circuit is 0.04 amps. I can also use my power equation, P equals I times V, to get the total power, which is 0.48 watts. So those 2 equations, Ohm's law and power equation, work for a column, but you can't mix and match, right? I can't use the total voltage with the resistance from R1 unless I have a good reason to do that. So you want to stay within a column for using those equations. So I now know something about the circuit as a whole. From here, the goal is to get another value in each one of those other columns so that I can solve them. This is where I start to think about my loop laws and my junction rules. This is a circuit with no junctions. That means the current through each of those resistors has better be the same as the current through the battery because there are no junctions. So I'm going to go ahead and just fill out 0.4 amps for each, 0.04 amps for each of those resistors as well. And now I've got 2 known values, and I can go ahead and use Ohm's law and the power equation again to calculate out the rest of the values. So I'm done mathematically pretty quickly, a lot faster than I would have been with simultaneous equations. But it's always a good idea to go back and look at each chunk of values and make sure that they make logical sense, consistent sense, and proportional reasoning sense. If you look at those voltage values, you should see that because the electrons have to go through 2 resistors, we're going to use some of that voltage at each resistor. And the total voltage better be equal to the voltage used at the 2 resistors. So you see 4 volts in the first resistor, 8 volts in the second, and the total is 12. That's a loop law situation, right? They sum to 12. You also should notice that each electron uses more of its energy in the higher or harder to pass through resistor, and we see that in the table. We use 8 volts of energy in the 200 ohm resistor and only 4 volts in the 100 ohm resistor. You also should note that the ratio of the voltage is the same as the ratio of the resistance. And so if you're really quick on your ratios, you actually can solve your voltage out even without using Ohm's law, etc. If you know that sort of the voltage has to be split into 3 parts, and 2 of the parts go to R2 and 1 of the parts goes to R1. That makes this solving this really, really fast. So that's kind of a shortcut if you can do it. Look at the I row, and you'll see that all of those I values are the same. We know this better be true in this circuit because of the junction rule and conservation of mass. If you look at the R values, you'll see that the total resistance is more than the individual values. That also makes sense because two resistors in series are longer than a single resistor, and therefore the total resistance should be more than the individuals. And then I always love to go back and double check the power. So whatever you've done everywhere else, your power should always add up by conservation of energy. So in this case, I see that 0.16 watts plus 0.32 watts gives me 0.48 watts, so everything worked out well. You'll also be able to use that column to predict which of your bulbs is brighter. That's really the only way to tell what bulb is brighter. You can't use resistance by itself, but ultimately, once you end up with your power values, you can say that R2 is twice as bright as R1. The reason why is because they have the same current, but twice as much voltage, therefore we're going to be twice as bright. Okay, so there you go, very fast solving a series circuit with a VIRP table. So how about solving a parallel circuit using a VIRP table? Set it up the same way you did before, and in fact, when you put your known values in, it actually looks exactly the same as the series circuit one that we did on the last slide. But that's where the similarities end, right? This is where you need to actually understand the physics, because you can't just add up those resistances to get the total resistance anymore. There's actually two approaches for this. Number one, solve for the resistance in parallel using the parallel resistance equation. Or number two, you can actually approach it from the individual resistors and then get into the totals eventually. The reason that I know that the voltage drop at R1 and R2 is also 12 volts is because those contain little mini loops, right, with just one resistor in the battery. Therefore, according to the loop law, the voltage drop has to be 12 volts at each one of those resistors as well. From there, you can calculate the remaining four values in the table using my Ohm's law and my power equation. And then you can use the junction rule to figure out what the total current is. If you know the current through R1 is 0.06 amps and the current through R2 is 0.12 amps, that means the total current coming out of the battery must be 0.18 amps by conservation of mass and the junction rule. Now we have two values in my total column, and you should be able to calculate the remaining two values. When we look at these rows to see if they make sense, as we discussed, the voltage row makes sense because of Kirchhoff's loop rule. Each of those resistors is in their own loop. The current makes sense because the junction rule applies. Since electrons choose a path, they're going to split. One note that the current through the smaller resistor is going to be bigger because there's an inverse relationship there. And you can use proportional reasoning with this as well. If you know the resistance is half as big, it's going to have twice as much current. So sometimes that's a shortcut to using the equations if you're really good with your ratios. The resistance value makes sense as well because the total circuit is going to have less resistance than either of the individual values. You see that we end up with 67 ohms of total resistance, which is less than the smallest resistor, which is 100. This is because there are multiple paths, electrons have choices of where to go, and essentially what we've done is we have increase the surface area of the resistor by putting another resistor in parallel with it. The power makes sense. Last but not least, you can always add up your powers to find your total power due to conservation of energy. And in this circuit, we find that it's actually the lower resistant bulb that is going to get more power and therefore be brighter because it has the same amount of voltage but more current. If you wanted to go the other approach and do the total column first, you could have used that equation to calculate the resistance in parallel directly. The way that would look when you set it up is 1 over R equals 1 over 100 plus 1 over 200. You end up getting 1 over R is 3/200ths, or R is 200 thirds, which is 67 ohms. So that could get you directly to that R value. And in any case, this calculation should confirm the calculation that we made using Ohm's law. Doesn't matter how you get your answer in physics, you know, multiple different pathways to the same correct answer. So occasionally you have complex circuits that contain some series and some parallel portions nested in each other, like this circuit shown below. This circuit can also be dealt with on a VIRP table, or you can do it with Kirchhoff's laws and simultaneous equations. But one of the important skills that you'll need to have is to realize how do we take the understandings of what happens in series and parallel and build them together to make a complex circuit. So any series portions of this graph have no junctions in them, and therefore the current is going to be the same through any portions of this circuit that are in series. So in this circuit drawn, it doesn't matter where the resistors are. The 3 ohm, the 6 ohm, and that 5 ohm resistor on the bottom are all in series with the battery, and therefore the exact same number of electrons every second have to be passing through all 3 of those locations. So I, for all 3 of those resistors, will be the same. The voltage is going to be the same across any parallel portions, because since each one of them is part of a different loop, right? And we already know what the voltage gained at the battery is, and the voltage, you know, is going to drop the same on each of the series resistors no matter which path it takes. That means that we have to have the same voltage at the top of that parallel chunk as we do at the bottom. Therefore, the drop across each of those resistors has to be the same. So for the 12 ohm and the 6 ohm resistor in parallel, the delta V is going to be the same for each of those values. And of course, the current will be different through the paths, but we'll have this. So when you are faced with one of these complex circuits, it is often a really good idea to redraw the circuit and simplify the circuit. This helps you to kind of like find a way into your VIRP table. And so this is often described as an equivalent circuit, an equivalent resistance. And so you sort of can imagine pulling out multiple resistors from the original circuit and replacing them with a single resistor that has a value that you can calculate. Usually I start with so you want to find a chunk of the circuit that is purely one or the other, purely series or purely parallel. In that first circuit, there's only one chunk that is kind of pure, and that's that parallel portion with the 12 ohm and the 6 ohm resistor. So you can imagine pulling that resistor out and replacing it with a single resistor, and you can calculate the value of that single resistor using your parallel resistance equation. So 1/12 plus 1/6 gives you 1/4. Take the reciprocal of that, and you can pull those 2 resistors out and replace them with a 4 ohm resistor. So I now have a circuit that's not quite the same, right, but it is equivalent in terms of overall resistance. From here, I can actually simplify one step further. Now I have a pure, simple series circuit, and I can actually imagine replacing all of those resistors with a single resistor with a single value. To find the value of that, of course, you just add up all of the resistances in series, and you end up with a 19 ohm resistor. So this final circuit is an equivalent resistance circuit to the original run. The reason this is useful is because you can use this equivalent resistance to find the equivalent or total current in the circuit if you know the battery, right? So that original circuit, you'd be like, well, I know the current's the same in the 3 ohm, the 6 ohm, and the 5 ohm resistor at the bottom, but I don't know what that current value is. I know the total voltage, but I don't know what the total current is because I don't know what the total resistance is. Well, now, by simplifying, we know the total resistance is 19 ohms, and you can then find your total current. That's really useful because your total current in the circuit is the same as the current in the 3 ohm resistor and the 6 ohm resistor and the bottom resistor, which will then allow us to calculate the voltage drop at each of those 3 spots. Once you've got those 3 voltage drops, well, the last remaining voltage drop is the drop across the parallel resistor. And so once you've got that parallel voltage drop, then you can solve for the rest of the values. So doing this equivalency often helps you get really important critical information that can let you solve these circuits using a VIRP table instead of having to use Kirchhoff's laws. Okay, we've reached the end of the video. Let's go ahead and review the essential question. This may be a repeat of a comic because I don't have the energy to check and see if it's a new one. But in any case, please review the essential question, which is how can I organize my data and use equations to predict the behavior of more complicated circuits? Thanks for watching.